and today I'm going to use the violin to talk to you about sound waves. How do instruments like this violin create music? Let's find out. Sound waves are caused by vibrating objects, and when you draw a bow across the strings of a violin, the strings vibrate as the bow creates friction. Plucking or bowing the string will cause a disturbance. That disturbance moves down the string as a vibration. It hits a boundary, a note, and it reflects back upside down. Compared with plucking the string, the bow allows the player to continuously input energy and so to maintain a note. This action of the bow drives the strings in a regular cycle of stick, slip, stick, slip. It involves some properties of friction, the force that makes things difficult to slide. Now that we know how sound is generated on the violin, let's learn how different musical sounds are made. Different musical sounds are affected by amplitude and frequency. Amplitude directly affects the loudness of a sound. When you apply less pressure with the violin bow, or pluck the string more lightly, the string vibrates less, causing a lower amplitude and thus creating a quieter sound. Versus, when you apply more pressure, you cause a higher amplitude in the string, which creates a louder sound. The harder you pluck the string or press down with the bow, the further the string vibrates. The frequency directly affects the pitch of a sound. When the wavelengths in a standing wave are longer, this means there will be fewer waves, which will mean a lower frequency and thus a lower pitch. When the wavelengths are shorter, this means there will be more waves, creating a higher frequency and thus a higher pitch. I will better explain this later with a simple mathematical equation. In the case of a string instrument, here the violin, the fundamental frequency depends upon a string's length, mass, and tension. Because of the length, mass, and tension of a string, this whole thing, the violin, literally is a mathematical breakdown of how to release a sound wave at each specific level of fundamental frequency for each string. Now let's break down this equation. Looking at tension, since tension is in the numerator of the square root, if it increases, so will the string's frequency. Thus, it will create a higher pitch. Now, looking at linear mass density, since linear mass density is in the denominator of the square root, if it increases, the string's frequency will decrease, creating a lower pitch. This is why thicker and heavier strings on the violin play lower frequency notes, and the thinner and lighter play higher frequency notes. Here I am plucking the G string and the E string to show you how the E string with the lower linear mass density has the highest level of frequency. Next time you listen to music, you might not think about amplitude or frequency, but you now know that behind this music are equations that engineers and scientists use to help these musicians perform that bring music to everyone, making the world a better place.